Let's study 9th standard ICSE, chapter number 1 of chemistry, the language of chemistry. Introduction. The first 5 paragraphs can be cancelled, they are out of syllabus. However, your school teacher may insist that you should learn the definition of chemistry. In that case, you do that. What is more important is this pink definition of an element. An element is a simple and pure form of matter which cannot be decomposed into simpler substances by any physical or chemical means. Centuries ago, people thought that water was an element. But today we know that it isn't, because if we pass electricity through water, it splits into hydrogen gas and oxygen gas, which proves that it is a compound. On the other hand, hydrogen or oxygen cannot be further decomposed or broken down by any physical or chemical means, although they can be broken down by nuclear means, but that is outside the scope of chemistry. So now we know what is an element, and there are totally 118 elements discovered so far. They combine in various ratios to form millions and trillions of compounds in the world. The next definition is of an atom. It is the smallest particle of an element, which may or may not exist independently, but can take part in a chemical reaction. Contrary to this, we have the definition of molecule, which is the smallest particle of a substance, which can be an element or a compound, and which does exist independently. We'll understand the difference soon. But before that, let's understand what is atomicity. The number of atoms in a molecule of an element is called its atomicity. For example, certain molecules are monoatomic. Take the example of noble gases like helium. One atom of helium is represented by He. One molecule of helium is also represented by He because it can exist independently on its own. It doesn't react, it doesn't combine with any other atom of any element. That's why sometimes atom and molecule may be one and the same. They are called monoatomic molecules. This is the case for metals also, like copper, magnesium. They can live alone. Even carbon is monoatomic, so their atomicity is 1. Next, diatomic molecules. Their molecules have 2 atoms, for example, hydrogen, H2, oxygen, nitrogen, and even chlorine, Cl2. So you can't find a single oxygen atom in nature because it's very reactive. A single atom would be unstable. Its octet is incomplete, last shell is incomplete. So it will definitely react with some other element or with oxygen itself to form O2 molecule, which is diatomic. Triatomic molecules have 3 atoms, tetraatomic molecules have 4 atoms, octatomic 8 like sulfurate, and so on. Now in the definition of molecule, we should mention smallest particle of element or compound, because this is a molecule of an element, but H2O is a molecule of a compound. Remember, compounds cannot have atoms. We can't have an atom of water. We can only have a molecule of water. This is the definition of compound. Cancel the next 3 paragraphs, even Dalton's symbols, and the next paragraph. And now we go to table 1.1. We need to learn the symbols of all the elements here. These are derived from Latin names. Carbon's symbol is C, but copper's cannot be C because that is already taken by carbon. We can't even use CO because CO stands for cobalt. So we are using the Latin name symbol Cu, which is for cuprum. Latin names are not important as per the scope of syllabus, but if your school teacher insists that you learn it, then you do have to. The rules of chemistry, the names of elements and compounds are all decided by IUPAC, International Union of Pure and Applied Chemistry. Symbol, the definition is, it is a short form that stands for the atom of a specific element or the abbreviation used for the name of an element. We know the examples already. Now, significance of a symbol. Cancel Roman number 3 here and here. A symbol like CO, it's a name of the element, that is cobalt, and it also defines one atom of the element. Note, capital C and capital O is a compound called carbon monoxide. More symbols which have to be studied. Valency. It is a measure of its combining power with other elements, but that's an incomplete definition. Cancel these 2 paragraphs. The perfect definition would be the modern one, which says the number of electrons that an atom or radical can lose, gain, or share during a chemical reaction. That's a complete definition. And the number of electrons in the last shell are called valence electrons. An atom consists of electrons, protons, and neutrons. Protons is the atomic number. Number of protons plus neutrons is called mass number. In a neutral atom, ideally, number of electrons and protons are equal. So amount of negative charge and positive charge is equal. That's why it's neutral. But if an electron is lost or gained, there's an imbalance in the charges, and that's when the atom becomes charged, and now we call it an ion. A positive ion is called cation and a negative ion is called anion. An ion is defined as positive or negatively charged atom or group of atoms because of loss or gain of electrons. In order to be stable, what would it do? It would give away that last shell electron, one electron, the valence electron, to achieve the stable electronic configuration of the nearest noble gas, which in its case is argon, which is 2,8,8. Since it is giving away one electron, we say its valency is 1. And in an ionic bond, its charge would be +1. Because after giving an electron, it acquires a positive charge. It would have more protons and less electrons. You see, an atom is neutral because the number of protons and electrons are equal. That is, the amount of positive charge and negative charge is equal. But after losing an electron, there is a deficiency of electron, and metals hence acquire a positive charge. On the other hand, let's look at sulfur. Atomic number is 16, so electronic configuration is 2,8,6. So in order to be stable, that is, acquire the electronic configuration of the nearest noble gas, that is, complete its octet state, the last shell, it would gain 2 electrons, so that it becomes 2,8,8. So when it gains 2 electrons, it would become negatively charged. It will form an anion. That's right, nonmetals form anions. And its valency is 2. Now, by that logic, think about it and tell me what would be the valency of aluminium. Ready? The valency of aluminium is 3. Did you get it right? You see, aluminium would like to lose 3 electrons to become stable. Metals usually lose electrons. Sodium has 1 valence electron. So to become stable and complete its octet and become like the nearest noble gas, which is neon, it would lose this 1 electron. That means it is deficient in 1 electron. Number of protons will be more. And hence, it is stable and positively charged. It's monovalent because its valency is 1. Magnesium loses 2 electrons to become stable. So it's divalent, valency 2+. Why positively charged? Because number of electrons are less than the number of protons. Remember, number of protons never change. That is always constant in a chemical reaction. Aluminium is trivalent because it would tend to lose 3 electrons to become stable and achieve its octet. Metals always lose electrons, so they are electropositive and they become cations. Non-metals have 5, 6 or 7 valence electrons, so they always gain electrons to become like the nearest noble gas. So they become negatively charged, they are electronegative and they form anions. But what if there are 4 electrons in the outermost shell? Well, carbon, which has 4 valence electrons, it's non-metal. But silicon, which has 4 valence electrons, is a metalloid. So there are other factors which come to the picture, like size of the atom, which you'll learn in 10th standard. Chlorine's electronic configuration is 2,8,7. Because its atomic number is 17, that means it has 17 protons in the nucleus and 17 electrons orbiting in shells. It won't lose 7 electrons, rather it will gain 1 electron to become a noble gas equivalent. This is like argon, 2,8,8. But now it has more electrons compared to the number of protons. So it's negatively charged. Its valency is -1. It's monovalent. Oxygen would gain 2 electrons to become stable, so divalent. Nitrogen would gain 3 electrons to become stable, so it's trivalent. And once these cations and anions are formed, opposite charges attract each other and they stick to each other because of electrostatic forces of attraction, and ions combine to form a compound. An ionic bond is formed, which we'll study in future chapters. For example, sodium is positive and chlorine or chloride is negative. They'll combine to form NaCl, a compound called sodium chloride with completely different properties. There is one more definition of valency, an old one. It is the number of hydrogen atoms that will combine with or displace one atom of that element or radical. Example, chlorine combines with 1 hydrogen atom to form hydrogen chloride, so valency is 1. Oxygen combines with 2 hydrogen atoms, H2O, so valency of oxygen is 2. Nitrogen combines with 3 hydrogen atoms to form ammonia, so valency of nitrogen is 3. Methane has carbon combining with 4 hydrogen atoms, so valency of carbon is 4, CH4. Variable valency. Certain elements exhibit more than one valency. For example, in some compounds, iron's valency is 2+, whereas in some compounds, iron's valency is 3+. The reason behind it is because iron does not lose electrons only from the last shell, but even the second last shell, the penultimate shell. The reasons for these we'll study in higher standards, but that's why variable valencies exist, so mark this as a GR. So the rules of octet and duplet are completely valid only for the first 20 elements which we have to study for our syllabus. But beyond the first 20 elements, the rules become more complex. There are many exceptions, but that is outside the scope of our syllabus. So when there are variable valencies, and all transition metals have variable valencies, then remember, the lower valency always gets the name us, and the higher valency gets the name ik. Nowadays, we name it like iron 2 oxide and iron 3 oxide, and not ferrous oxide, ferric oxide, which makes it even easier. So copper 1 oxide means copper with 1 valency, and if you know the crisscross method, you will be able to write the formula. Even non-metals can show variable valency. For example, nitrogen has valencies 3, 5, sometimes even 4 and 1. Sulfur shows 2, 4, 6. How does that work? Well, that we need not know right now in 9th standard. Learn this table. Formula, first paragraph cancelled, and let's learn the definition. Molecular formula or chemical formula, it uses symbols to denote the molecule of an element or a compound. For elements, we have H2, O2, these are all molecular formulae. And for compounds, we have NH4Cl and all. These are examples, we know that, so we can cancel it. Even this can be cancelled. Radicals, first paragraph cancelled. Let's understand the definition. It's an atom or a group of atoms of the same or different elements that behave like a single unit with a valency. Cancel positive or negative charge. So for right now, just imagine that ions are also called radicals. So these are all cations or positive ions or basic radicals, and most of them are metals except ammonium and hydrogen. Everything else is a metal. And the negative ions or anions or acid radicals, these can also be called as radicals. So charged particles are called ions, and they can also be called as radicals. But the truth is, all ions are radicals, but all radicals aren't ions. However, we need not know those exceptions right now. First, the compound's name is ammonium carbonate. So ammonium, we write NH4 1+. It's ammonium, not ammonia, by the way. And carbonate, CO3 2-. You will remember these values if you learn this table very well. See here, carbonate, anions are always on the right hand side here, and ammonium is out here, NH4 1+. The signs won't be mentioned in the final answer. So this +1 goes to carbonate, and the 2- goes to ammonium. So finally we have NH4 2 CO3, and the 1 need not be written, it's understood. But this 2 belongs to the entire ammonium ion. That is for nitrogen as well as for hydrogen. So put brackets out here. So this is the final answer. No signs required. Notice how this subscript was not affected at all. That remains as it is always. That doesn't shift or change. So in this molecule of ammonium carbonate, how many nitrogen atoms are present? 2. And how many hydrogen atoms are present? 4 into 2, 8. How many carbon atoms? 1. And how many oxygen atoms? 3. Now, try to solve calcium dichromate. Notice how these numbers can be cancelled. So whenever you can reduce the numbers, you should. So now what is left is 1 and 1. So no need to write it. So the final answer is this. Next, what about platinic sulfite? First, we'll try to reduce the numbers if it's possible. Yes, it is. So 2 1s and 2 2s. So now this 2 comes down and the 1 comes down here. 1 we need not write. So I'll just write a PT and sulfite SO3, and the 2 is for the entire ion. So I'll have to use brackets. But what about magnesium nitride? Well, just crisscross. 3 comes here, 2 comes here. So that's Mg3N2. No need for brackets because we have just a single elements out here. Here we have 2 elements combined together, sulfite. And the 2 number is for both of these elements. So we should not discriminate. We should put the brackets stating that the 2 number is for both of them. So that's how we'll solve a few sums in the exercise later. Simple radicals are made up of only one type of atom or ion. Compound radicals have atoms of 2 different or 3 different or more than that elements combined together. These are examples which have to be read. You need to learn these tables by heart perfectly. Then you would be able to write the correct chemical formula of any compound in our syllabus and frame equations in the future. One correction is that aluminate's valency is not this. Cancel it, and this should be aluminate. Cancel page 7 entirely. Here they have taught how to do the crisscross method and write formulae. Now there are some rules to follow while naming certain compounds. Whenever a metal and a non-metal combine, the non-metal's name changes. First of all, we always write metal first, and only the non-metal's name changes. Why? Because the society is like this. There is discrimination. Can't help it. So nitrogen becomes nitride, oxygen becomes oxide, sulfur becomes sulfide, chlorine becomes chloride. But calcium, sodium, potassium, their name doesn't change. That's patriarchy at work, I guess. Two nonmetals, well, yeah, nowadays even nonmetals combine with each other. It's a democracy, it's allowed. Phosphorus trichloride, phosphorus pentachloride. So we use prefixes like tri and tetra. If two elements are combining with oxygen, then the name depends on the number of oxygen atoms present. For example, in hypochlorite, we have less than 2 oxygen atoms present. That is 1. If there are 2 oxygen atoms present, then we call it a chloride. 3 will make it a chlorate. 4 or more will make it a perchlorate. Certain acids' names have to be learnt, like hydrochloric, hydrofluoric acids, sulfuric acid, nitric acid, phosphoric acid. But if we have an acid with a little less number of oxygen atoms, then we use us instead of ic. For example, this is sulfurous acid, not sulfuric. This is nitrous acid, not nitric. Trivial names. Well, these are common names used, which don't have any particular rules. NH3 can be technically called as nitrogen trihydride, but we call it ammonia. Dihydrogen oxygen, or dihydrogen monoxide can be called as water. We need not learn the chemical name at all. Section 1.8 is not supposed to be in syllabus, so just mark it as read, but your school teacher may insist that you learn it. In that case, you have to. If they give you a formula and ask you to find the valency of an element, like they give you NO2, and they ask what is the valency of N out here. Now, typically we know the valency of N is 3, but that is only for ionic compounds. That's straightforward. Here, it's a covalent compound, so things get more complex. Variable valency is possible. We start with oxygen. Let that be 2. Yep, oxygen's valency is always 2. Now, if you say nitrogen's valency is 3 by the crisscross method, it won't work out. So what number should I write here so that I get the final answer is NO2? Well, it will be 4. Because only if N is 4 and O is 2, will I be able to cut first of all, 2 1s are, 2 2s are, then 2 comes down here and 1 comes down here, and finally I will get NO2. So now assignment for you, N2O. Calculate and tell me what is the valency of nitrogen in this compound and type it in the comments. Next, chemical equation. Well, it is a symbolic representation of a chemical reaction using symbols and formulae of the substances involved in the reaction. That is, the reactants and the products are shown. All of this is cancelled. We know what are reactants and products. So here, these are the reactants on the left hand side and these are the products on the right hand side. Now, chemical reactions. If they ask you, write any reaction in which we have 1 reactant and 2 or more products, then you can write either example. Here we have 2 products, here we have 3 products. On thermal decomposition, it's a decomposition reaction, they break up into smaller compounds. This reaction will be repeated in other chapters as well. If they ask you, write an equation with 2 reactants and 1 product, that's called a combination reaction. And these examples will be valid. Although other examples will also be allowed, but make sure that they are correct and they are balanced. If the equations are not balanced, then we don't get marks in exam. By the way, this second example, that's a very famous equation called the Haber's process to form ammonia. It will be repeated in hydrogen chapter. And the first equation is interesting because I see 2 gases, a base and an acid, a gas. They are reacting to form a solid, in fact a sublimatory solid, ammonium chloride. So I'll see dense white fumes. That's an observation. Next, equations in which 2 reactants give 2 products. So this is double decomposition or double displacement reaction where silver goes with chloride and sodium goes with nitrate. They exchange their radicals to form 2 new substances. And here, one of them is insoluble, so we call it a precipitate, hence the down arrow, or you can even write PPT. And the other one is soluble. By the way, this is a white precipitate, and even here it's a white precipitate. So these equations will be repeated in the future with colors. Next question, given equation in which 2 reactants and there are 3 or more products. Well, the Bravo one is too complicated, so just learn the alpha one, that's enough. Skeleton equation is cancelled. Balanced equation, that's easy to define. An equation in which the total number of atoms of each element of the reactants is equal to the total number of atoms of each element of the products. So don't miss a single word here, then only it will be a perfect definition. But why should we balance the equation? Well, if we don't balance the equation, then the number of atoms will be unequal. But that is against the law of conservation of matter, which says that matter can neither be created nor destroyed. So from where did the extra atoms come? Or where did the atoms disappear? But if it is balanced, then no such contradiction happens. Then they teach us how to balance a chemical equation. We can cancel all of it because we're going to study that in numericals. Cancel this entire page and even this entire page. And even here, cancel this. Everything is cancelled on this page, including this top part. The only thing which is there is limitations of a chemical equation. Even here, cancel A, C, D, F. So we have just 3 points to learn in limitations. In a chemical equation, we don't get to see the time taken for completion of the reaction. We don't know what is the rate of the reaction by just looking at an equation, and we cannot find out if the reaction is complete or not by just looking at an equation. Next, we have the concept of relative atomic mass, or also called as atomic weight. It is the number of times one atom of the element is heavier than 1/12 of the mass of a carbon-12 atom. Let's take an example to understand this. First of all, consider these atoms. This is a hydrogen atom. Its atomic number is 1 because it has only one proton. And its mass number is also 1 because it has only one nucleon. That is, the number of protons plus neutrons is 1. In fact, it doesn't have any neutrons. The number of electrons doesn't affect the atomic number or the mass number, although the number of electrons will always be equal to the number of protons in an atom. Let's take another atom. Let's say beryllium. Its atomic number is 4. So it has 4 protons, and interestingly, it has 4 neutrons as well. It's not necessary that the number of neutrons have to be equal to the number of protons, but here they are. So what is the atomic number? 4. It's the 4th element in the periodic table. And what is the atomic weight or atomic mass? Well, it's 4 plus 4, 8. And for carbon, its atomic number is 6, and atomic mass or atomic weight is 12 because it has 6 protons and 6 neutrons. So looking at these diagrams, it's very easy to identify the atomic number and the atomic weight. Atomic weight or atomic mass is simply the sum of the number of protons and number of neutrons in the nucleus. Together they are called nucleons. But when we talk about the relative atomic mass, first we consider the mass of a standard atom, and we have chosen, or rather scientists have chosen, the carbon atom as a standard. So what is the relative atomic mass or atomic weight of a carbon atom? It's 12, isn't it? It's 12 AMU, that is atomic mass unit, but nowadays we call it Dalton. Next, we take 1/12 of it. So what is 1/12 of the mass of a carbon atom? Yes, it is 1. And now tell me, how many times is beryllium atom heavier compared to the number 1? That is, how many times is 8 compared to 1? Well, it is 8 times. Or simply speaking, the beryllium atom's mass is 8 times 1/12 the mass of a carbon-12 atom. By the way, we are not even counting the mass of the electrons because their mass is so small. Approximately 1,800 electrons mass is equal to the mass of 1 proton. So we just focus on protons and neutrons, which have almost the same mass. So when you ask me the atomic weight of beryllium, I can just look at this and I can tell you it's 8. Let me give you an oxygen atom. Atomic number is 8. And if I say that the oxygen atom is 16 times heavier than 1/12 the mass of a carbon-12 atom, then what is its relative atomic mass? Well, no wonder it is exactly 16. And an easy way to remember this is, in an oxygen atom, it has 8 protons and 8 neutrons. But again, this is just an approximate number. The actual atomic weight of oxygen is 15.99. So the values we learn at school level are all integers, no decimal values. And we learn an easy way to learn the atomic mass, the number of protons plus neutrons. But the relative molecular mass of water is, well, it has 2 atoms of hydrogen plus 1 atom of oxygen. Hydrogen's atomic weight or atomic mass is 1 and oxygen's is 16. So this comes up to be totally 18 atomic mass units. So that's the relative molecular mass of water. But as far as the scientific definition is concerned, we would say that 1 molecule of water is 18 times heavier than 1/12 the mass of a carbon-12 atom. Now, I have a challenging question for you. If you look at the periodic table, or even if you Google it, you will notice that chlorine's atomic number is 17 and its mass number is 35.5, which is very strange. Mass number is approximately the total number of protons and neutrons. How can we have a decimal value for it? Well, if you can find the answer, leave it in the comments. Similarly, we can understand the definition of relative molecular mass or molecular weight as well. cancel all of this. And even here, apart from the definition, everything else is cancelled. Now, percentage composition. So we will study this when we study the numericals. Now, empirical formula. Well, that's not in syllabus, but still I'll explain how to solve it. Cancel the definitions though. If you're given a compound, C6H12O6, empirical formula means the simplest form. So if you can cut with all the elements, then cut it. 6 1s are, 6 2s are, 6 1s are. So we can reduce it, and the final answer is CH2O. Interestingly, if I take acetic acid, even here, first of all, I'll write it in the standard form. 2 carbon atoms, so C2, 4 hydrogen atoms, so H4, 2 oxygen atoms, so HO2. Now, if I reduce it, and it should be able to be cut with all elements, okay, not just 2 out of them. So then the final answer is the same. For H2O2, the empirical formula will be HO, but for H2O, we cannot reduce it further. It's the simplest form. So this itself is the empirical formula. Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.